So now we have touched upon the basics of power electronics. It's just a basic introduction of power electronics. Now I think we are ready to understand that how this field of power electronics look like. Means if somebody wants to go into details of power electronics, like want to go into the research or do research in power electronics. So it's better to understand that it is a multidisciplinary field. So if you want to go into a research of power electronics, how to do that. Power electronics actually has grown into a multidisciplinary field due to advances in power semiconductor or semiconductor devices, because you know that semiconductor devices have evolved over the last 7 decades. So nowadays we have very sophisticated semiconductor devices. And then advances in microelectronics, just like VLSI chips. Nowadays, this single VLSI chip or a single DSP processor can actually execute several mathematical calculations in microseconds. And this VLSI chip technology can actually integrate millions or billions of transistors on a single chip. Billions of transistors on a single chip are possible. So due to these advances in these technologies, this power electronics has grown into a multidisciplinary field. Means if somebody wants to design a power electronic circuit, they can work in this power semiconductor devices or doing research in this or doing research in VLSI. That why not integrate inductances, capacitances, or other means active as well as passive switches on a same single silicon chip. So people are doing research in that area so that cost can be minimized, losses can be minimized, and efficiency becomes higher. So microprocessor and microcontroller. So making efficient or designing efficient algorithms and putting it on microprocessors and microcontrollers on the same silicon chip. On the same VLSI chip, this microprocessor and microcontroller can be implemented. And then efficient algorithm can be realized on the single or same microprocessor. So means in one single chip, you can have switches, semiconductor devices, other electronic circuits, and the controller algorithms. And these are possible already. But people are doing research to make it more efficient. And then doing research in areas of finding new developments in control algorithms. So design upgraded or sophisticated control algorithms, so that just by using these sophisticated and efficient control algorithms, you can save power losses. And new demands for new applications keep on coming every day. And then how to deal with these new applications. So people are doing research in that area also. So new applications have new challenges. Then how to deal with these? So due to all these advances, we can deal with the new applications. So what are the benefits? Just by using these advances, we can get these benefits: higher efficiency, high reliability, because no movable parts, only static parts, lower system and maintenance cost, because due to this, we can have less wear and tear, so low maintenance cost, and system cost also, means design costs are lower. Faster response time, because these switches operate in megahertz range also, so response time is fast. So the operation time is faster. Configurable, because of these microprocessor, microcontroller, and DSP and VLSI, all these, it can be configurable. So configurable means it can easily be changed according to our need, according to our requirement, or according to our desires. easily configurable. And based on these advances, these systems can be smaller in size and less in weight. These are all the benefits. So now graphically, the same thing which we have shown in the previous slide. So if a power electronics engineer, that person can do research in this, in simulation and computing, signal processing, getting new algorithms, analog electronics, new circuits, analog and digital circuits, microcontrollers for low power and low losses, high efficiency. Control algorithms can be implemented in microcontrollers, and at the same time, microcontrollers can be dedicated microcontrollers can be designed for that. Electromagnetics, L and C, that how inductance and capacitances can be optimized. System and control theory, to find out efficient control algorithms to control power electronic circuits for higher efficiency at the output. Electrical machines, but how to interface this this power electronic circuits for efficient running of running and control of or speed control of electrical machines. Power systems. So power losses, we keep on hearing huge power losses in power systems or power transmission, power distribution. And then instability problems, a lot of faults, load sheddings. So we can design some of the efficient power electronic systems so that these things can be minimized. These issues can be minimized in power systems. Integrated circuits, that how to integrate all the power electronic circuits in a single chip. Then designing new semiconductor devices. We'll see what type of semiconductor devices are in use in power electronics when we talk about the power semiconductor devices in next lectures. So now, after this, now we have come to this applications in real world. So these power electronics have some useful applications. Before going into the applications, I just have to, I think, make it clear that in the conventional power systems, these things we keep on seeing whenever we have hurricanes or strong winds or floods and all this. So a lot of damage to the power system. We can easily see that almost every year. So what to do? So it's better to stop challenging the nature. So it means we can be more friendly. How to do that? We can use power electronics. So how to do or how to make these power electronic systems useful? By generating the power locally, just like microgrids. So if we have a small community over here, let's say like this is a, so why not have a dedicated small grid over here which can supply power to all the households in this locality only. So in that case, it can be efficient. Renewable power resources can be used. So we can reduce the dependency on power, fossil fuels. So thereby we can say that all these emissions, the dangerous emissions, the carbon footprint, greenhouse gases, radioactive substances, all the pollution which cause hazard to human health or environmental health. So we can get rid of all these problems just by making a small grid which can accommodate all the households in the locality for power flow. And at the same time, this power flow will be efficient because we don't have to transmit this long distances, which may cause instability, loss of power and all this. So one example I'm showing over here. So this is one simple example. Either every household has a solar panel and then they can run their complete household just by this solar panel. And each house has its own solar panel and they run their power in house using this solar panel. Or there may be a microgrid somewhere here which can supply power to all the households over here. And we have a solar panel somewhere here, a microgrid here, and that microgrid can supply power to all the houses in the vicinity of this neighborhood or in the same locality, depending upon the size of the locality. So these types of power systems like microgrids are already in place in several parts of the world. Not in mainstream, but still they are available. So some nanogrids are also possible. So some of the big organizations, they have their own nanogrids or microgrids, so which run the power supply for their own organization, so which covers about few acres of land. So it's possible, just like a university system, which covers about 500 acres or so. They can have their own microgrid, which covers the complete power system of a university. It's possible. So it's possible by using microgrid. So I'll show you. So this is a very, very important example application. So now I will be talking about each and every application. And then first of all, before going into these applications, I think I must categorize these applications as static applications or drive applications. Static application means where non-rotating or moving mechanical components are involved. So no moving mechanical components or no rotating mechanical components, such as power supply. UPS means uninterruptible power supply. Power generation like HVDC, high voltage DC transmission, flexible AC transmission systems, welding systems, heating systems, cooling systems, electronic blasts. So these are static elements. Just by using static components, we can use these power electronic systems. Another one is drive applications. Contains moving or rotating components such as motors. Electric trains, we make power electronic system by using static switches or static devices, but for movable applications like electric trains. Electric vehicles, air conditioning system, where we are running the motor and a compressor, pumps, compressor, conveyor belt, and so on. So these are the two categories of power electronic applications. And these, both these application categories, they have efficient use of power electronics. And we know that these applications ranging from few watts to megawatts or sometimes gigawatts. This is one basic example everybody knows. This switch mode DC uninterruptible power supplies, or we call it a charger or adapter, taking input from the AC line voltage, converting it to DC through a rectifier, filtering out the ripples, and then stepping up or stepping down the DC, because here we have a DC and we remove ripples from DC by using this filter. And then once the ripples are removed, we can step up or step down the value of DC and send it to the load, which can be a laptop or a mobile phone or something. So now electric drive applications, these are the applications which I showed in the previous slide. So this is one simple application, a drive application. This is the conventional drive, where we have a motor at home connected to the mains, the line input, and the pump is being run by the motor. It takes the inflow of water from here and it sends at the output, and maybe some storage is here, and it keeps on storing and it pumps out the water from here and sends it to the storage tank over here. And the valve is actually the controller over here. It controls the flow of the water only from this direction. And from this direction, there is no flow of water. That's the only control that this throttling valve is doing. So only one way flow of water. But if we have an adjustable speed drive over here, that depending upon the water flow, that how much water needs to be flowed over here, we can adjust the speed over here. So this adjustable speed drive based on the block diagram which we saw in earlier slides, where we have a power processor and a controller. So that is, at this moment, just remember that block diagram is already built inside this. It has a motor, and with the motor, it has a block diagram of a power processor and a controller. So it controls the speed of the motor. Based on the speed of the motor, the pump speed is adjusted. So based on the speed of the motor, the pump speed is adjusted. So if this pump speed is changing, the input flow will change and the output flow will change. So input flow is there, but output flow will change. The flow at the output of the pump will change. So it sucks the variable amount of water from here and sends it to there. So we don't need valve over here. Just by changing the speed of the motor, the change in the water flow will happen over here, depending upon our requirement. So this is very, very basic example and a classical example of a power electronics. So the same block diagram, you have to remember, is already inside this adjustable speed drive along with the motor. Another example, AC drive. So we have again the same thing, AC supply, a rectifier over here, and L and C components, which controls the energy storage. And then this energy stored over here, it runs the inverter. So it converts DC supply over here to the AC supply over here. Yes, so this is a AC supply over here. And based on this one, this control circuit will adjust the switching or the, here, this is a power processor. You remember one power processor which converts DC to AC. This is another power processor or power converter. So this power processor has one AC to DC converter, another DC to AC converter. So this DC to AC conversion is controlled by this controller. This controller adjusts its control signals based on the feedback it receives from here. So if we want to increase the speed of the motor, this motor, AC motor over here, which can be an induction motor, if we want to increase or increase or decrease the speed of the motor, the speed sensor over here senses the speed and compare it with the reference. If this speed is lower and this reference speed or set speed is higher, this control signal knows that actual speed of this motor is actually slow. The required speed from this knob is higher, so I have to increase the speed over here. So the difference of these two signals will be calculated by the controller, and the difference is sent over here. And now this switching frequency of the power inverter will be changed or adjusted, and we get a actual value of the speed of this motor, same as the speed over here or a required speed over here, just by making the difference of this and this. Sorry, this signal and this signal. Every time it is compared, every time it is sensed, and it keeps on iterating. And let's say after 10 iterations, this sensor over here, which can be a speed sensor, this speed sensor gives the value over here, which is exactly the same as this one. So now there will be no difference. This control signal will send that there is no difference. So no further change in switching or adjusting of the switches is required. So no changes. So this power inverter will keep on running for always. So this is possible due to efficient control algorithm and an efficient power electronic circuit. So these things, that variable AC drive is actually used in refrigerators, air conditioners, and washing machines, and so some other applications also. So now, one application, I think it's better if this is one classical and general application. Now taking an example of air conditioner, this one. So this is a power electronic converter, AC to DC and then DC to AC. And DC to AC, we have inverter over here. Before that, it is a rectifier. So let's say that power processor is here. It gives us the AC signal, which runs the motor, AC motor over here. It runs the air conditioner. And based on the cooling, it measures the temperature and humidity and sends, measured by using sensors, and sends this signal to the controller. Whatever is calculated over here is sent to the controller, and this is the desired temperature and desired humidity. So we normally set some value on the air conditioner to temperature of 20, let's say. Temperature of 20 is set, for example. So that is the desired temperature. And this is now the calculated or actual temperature. So both of these are compared. So if there is any difference, this controller will send the signal to adjust this switching power converter over here, which adjusts the speed of the motor. In turn, it adjusts the air conditioner and then the cooling. And then again, this value is calculated and by the sensor and send it to the controller. And when this desired temperature is same as this calculated temperature after several iterations, now system controller will see no difference. So it will send this is okay now. So we don't need to increase or decrease the speed of the motor. It can go to some low power mode, the air conditioner, and then the same cooling keeps on happening. And then we can say we do not need to change anything further unless the desired temperature is changed or any disturbance comes from the outside, like opening of the door or something like that, or more heat is coming at this. So then this signal over here, then this signal, it will see the change in temperature due to the opening of the door or some other disturbances. And then this one will be changed, and this desired is always fixed. So another difference this controller will see, and then gives this command to this converter to change the switching frequency, change this motor and all this. So just by making the power electronic circuit and a control algorithm, efficient control algorithm, we can actually do it faster. Maybe within 1 or 2 iterations. If this control algorithm is very efficient over here, inside the controller, there is an efficient algorithm, maybe within 1 iteration, this difference between desired and actual is 0. So this is called error signal. So maybe this error signal becomes 0 in 1 iteration only. And then we do not have to consume power in running iterations all the time. So depending upon the efficiency of the algorithm over here, efficiency of the switching converter over here, we can actually save the power and increase the efficiency. So another example is the fan regulators. In previous regulators, we were having rheostats, having resistances. They consume power, increasing the electricity bills. But nowadays, we have a triac-based or a switch-based, semiconductor switch-based regulators. So no resistance. So semiconductor switch-based regulators, and we can easily make the changes in the knob, which are just detected by the triac over here, and it efficiently changes the output without any losses in the resistance. So only conduction losses in the triac, which are very, very low compared to the resistance losses. We'll see later on. So from here, we can easily save a huge amount of power. So every day we save some amount of power calculated for 365 days, let's say example. So we can save a large amount of power. And if there is a huge organization where they have hundreds of these regulators, so multiply by 100, they can even save a large amount of power. So this is very, very basic example and an important example of a, or application of a power electronic circuit. Another is CFL. Again, power electronic circuits over here, this input supply from mains. We have a rectifier with the C filter, means it removes the ripples also. So here we receive DC with removed ripples, half bridge inverter also. So here we have a DC. Now DC to AC, we get AC over here, LC tank over here. So LC tanks are actually, again, the same thing. They store the energy depending upon the requirement. And now it is sent to the CFL actual. And now we have a sensor over here which senses the current. And based on this current, we actually calculate the brightness level. And this brightness level is given to the control circuit. And this is the reference brightness, means the desired brightness. Both of these are again compared. If there is any error between these two, error means any difference between these two, we get a signal to change the brightness. If there is no difference between the desired and the actual calculated value, so this control signal sent is that no need of further change is required. So it will keep on operating on the same value. So based on our own desired brightness, we can actually get the desired brightness just because of power electron, nothing else. So using this circuit, we can actually save 20 to 30% of power just by doing this. Again, the same thing for LED. LED also the same thing. Mains supply, we have a filter, this rectifier with a filter, let's say, by removing the ripples. We have a power factor correction circuit. Next slide, I will talk about this power factor correction circuit. And we have a current regulator. So based on this power factor correction circuit, we regulate the current. Regulate the current means either increase the current or decrease the current. So if we increase the current, the brightness of the LED will increase. If we decrease the current, brightness will decrease. So just by using the rectifier over here, and we can use the feedback also over here. But if we correct the power factor over here, so we can have an efficient current value over here, which runs the LED. So this is the power factor correction circuit. So let's say this is a CFL, has inductance and resistance. We have a supply over here. And we know this is the active power PL, QL is the reactive power, S is the apparent power. The apparent power we know is active power plus the reactive power. Reactive power is actually the imaginary component. So this is imaginary. And the power factor is cos theta 1. This we already know by definition. Theta is the angle between the active power and the apparent. So this is the power factor cos theta 1. Now, how to correct this power factor or change this power factor? We just insert a capacitor in between. If we insert a capacitor in between, this one was before adding a capacitor, like in the previous slide. Power factor was cos theta 1. Now after adding the capacitor over here, this apparent power comes out to be, active power remains the same because capacitor and inductor, they only contribute to the reactive power. Resistance contribute to the active power. So this remains the same and the reactive power now changes. So QL was the reactive power due to inductance and QC is the inductive reactive power due to capacitance, which is the on the other side of the means it is displaced by 90 degrees. So that's why it is minus sign. So this QL minus QC will be the new reactive power. So if we have a leading angle of current over here due to inductance, we have a lagging angle due to this. So it can be balanced. But let's say it's not completely 90 degree, but this is due to inductance, that is due to capacitance. So the difference between these two will give us the reactive power. So the difference between QL and QC will give us the reactive power currently. So now we have another theta, which is theta 2. So this theta 2 will give us the power factor. So cos theta 1 and cos theta 2. So in this case, cos theta 1 was higher, theta 1 was higher, theta 2 is lower. So cos theta 2 will be, if we are taking cos of all these theta 1 and theta 2, this value cos theta 2 will be more. Let's say it is 30 degrees, this one is 60 degrees. So cos 60 degree and this is cos 30 degree. Cos 30 degree equal is higher, cos 60 degree is lower. So we have increased the cos factor, means cos theta is the power factor. So just by including capacitor, we have increased the power factor. So we have increased the power factor. So if we increase the power factor, the reactive power becomes smaller or lower. And that's the whole idea, to make the reactive power lower or zero. Ideal, it should be zero. So all the apparent power is equal to the active power. But in this case, we have actually increased the power factor. By increasing the power factor, we actually save the power. The efficiency becomes higher. We'll see when we talk about the power converters. So just by including capacitor in between, we increase the power factor, and by increasing the power factor, we increase the efficiency or we decrease the losses. This is another example. Fuel cell energy systems, stack of cells, we get DC. And now here we have a DC from fuel cells. We have a DC to DC converter, which converts the level of DC, step up or step down. And then after this stepping up or stepping down of DC, we convert it into AC, remove the ripples, and we run into the AC grid, like a microgrid. So we can run a microgrid just by using fuel cells. And actually people are using it in small hospitals or small organizations, small factories, small schools also, they are using it. In Western world, mostly they are doing it. So, okay, so now after this, I think it's better to give a few applications for power electronics in power systems. Power systems nowadays, because we have some issues because of the growing consumer demand for power. Nowadays, demand of power consumption at home keeps on increasing due to multiple air conditioning systems at home and a lot of other equipments at home or in factories or in organizations. So demand is growing. So, and at the same time, complexity is also growing because different grids are being connected to different grids. And due to this, the interfacing or integration, complexity increases. So stability also gets disturbed. If interconnections of different grids happen, the stability increases. Means the stability issues increases due to the active and reactive power imbalances. We saw in last slide that how active and reactive power look like. So they keep on getting imbalances every now and then. Means every few kilometers there is an imbalance between active and reactive power. Somewhere the capacitance values are more. So if let's say if there is a transmission system for a few kilometers, the capacitance value is different than another length of a transmission system. Inductance value can also get disturbed. And if inductance and capacitance value keeps on getting disturbed, QL minus QC will disturb. And if QL minus QC will disturb, cos theta will disturb. The power factor keeps on disturbing itself. And due to this, imbalance between power sharing or power distribution is because it causes instability. And due to this, there are loss of power. There are lots of power losses and stability problems, causing further faults in the power systems or damages in the power system. So we need to get rid of these. So high power transmission power losses, yes. Then voltage instability, as I told, due to the imbalances between QL and QC. Inability to utilize power distribution. So again, the same thing. If there are imbalances between inductance and capacitance values, the power factor keeps on varying itself. Due to this, reactive power due to inductance and capacitance keeps on varying. Again, the same concept. So that is the basic concept and the most useful concept. So inductance and capacitance value keeps on changing, impedance keeps on changing. So due to impedance, power losses keeps on changing or imbalancing itself. Due to these imbalances, stability becomes a problem. The system becomes unstable. That is power loss. Another one is due to capacitance and inductance value changes, QL and QC changes, means the reactive power due to inductance and capacitance changes, which causes imbalances. And these imbalances cause changes in power factor. And definitely due to this, the instability occurs. So how to get rid of this? One is go for HVDC transmission. So it means if we want to transmit high voltage AC from, let's say this is a thermal plant, it generates and sends it to some long distances over here, and it generates AC and we get AC at the output. So if we do that to transmit generated AC, high power AC to high power station somewhere long distances, so there are basically that we need several lines to carry the AC signal. Three phase, normally it's three phase. So we need three phases or three conductors of lines connecting together. So connecting this transmission to the receiving part over here or distribution part over here. And one neutral conductor is also required. So that is one problem. Another problem is, as we have seen earlier, that due to transmission of AC for long distances, inductive reactance imbalance can be there, which can cause instability. Capacitive reactance imbalances can also be there. They also cause instability. So these are the main disadvantages if we want to transmit the high voltage AC to high voltage distribution system long distance away. So imbalances due to variation in inductive and capacitive reactance. Due to impedance, we have power losses for long distances because the impedance becomes larger. And at the same time, we need three phase conductors and one neutral. So if we go for high voltage DC, so what do we need to do? We need to first convert this high voltage AC into high voltage DC through rectifier, transmit through long distances, and send it to inverter over here, which converts this DC into AC. So only two conductors are required, positive and negative terminal. But compared to the four terminals, the four conductors for AC. But we can even save the ground terminal also, the negative terminal. So this negative terminal can be connected to the ground. So we can require only one conductor. So we can save a huge cost on conducting these transmission conductors. Another one is because we are talking about DC. So this drop due to inductance is zero because the rate of change of current in inductance is zero. So imbalances due to inductances can be minimized. So no instability problems can occur. And this QL minus QC will not cause any problem. Power factor problem or power factor imbalances cannot occur. So we cannot have unstable issues in high voltage DC transmission. So all the benefits, and at the same time, there is another benefit. So it can be bidirectional. So this can, for bidirectional purposes, this can now be used as a rectifier. So means input of AC over here and output of DC over here and transmitting to this part. And now here we receive DC, converted to AC, we get high voltage AC over here. So this can work either as an inverter or a rectifier. This also as a rectifier or inverter. So this is another benefit. So that's why this power electron, this is all possible due to power electronics, power converters. So using this power electronics, we can save huge losses compared to the conventional power systems. This is the first application of power electronics in power systems. So this is the second application. Again, the same thing, stability problems. So a lot of, you can say that, because if we just use this is the sending part, this is the receiving part, like in the previous case. So this is pure AC now. So all the AC conductors are required over here. May not be long distances, a small distance. And we just put a power electronic circuit over here. So this power electronic circuit, the only thing is, because of all the imbalances of inductances, power factors, impedances, we have all the problems of instability and all this. And at the same time, due to all these imbalances, we have all huge losses, means a lot of power losses happen during the power flow. But if we include this FEPS controller over here, which is flexible AC transmission system, again using the power electronic circuits inside it. And we'll talk about this FEPS system when we talk about the these power converter systems. So after 2 or 3 lectures, we will be starting these power electronic systems or power converter systems. And then one of the application is FEPS controller. So we will be dealing with this FEPS controller also when we do the applications of it. At this moment, is the main important part is that how to understand about the applications. So this will actually improve the capability of this power system, so that the maximum power is transmitted with minimum losses in between. And how to do that? To get a control over here, so that we can control the reactances and impedances in between. And we know that from HVDC side or from power factor correction side, due to the imbalances between inductive reactance, capacitive reactance, and impedance of these lines, the instability occurs, and at the same time, high power losses occurs. So we can reduce these power losses and instability problems just by making a controller over here, so that we can control the disturbance in these reactances and impedances. Another name for this is a compensation. So we can compensate the disturbances in the reactances. So how to do that? Using this FEPS controller. So FEPS controller is just a compensator inside it, just by using the configuration of capacitances and inductances. And one classical example is the power factor controller. That is also part of the FEPS controller. So power factor correction is the part of a FEPS controller. And others we will do when we do the application parts in detail. So it means that using power electronic circuit, we can actually control these power systems also for higher efficiency, because we minimize the losses. To minimize the losses, we actually get the high efficiency. This is again the example for this PV system, means photovoltaic system, also called solar panels or solar energy. So this is photovoltaic panels or modules. So we get the DC over here. We have a charge controller over here, interface between this solar panel and in batteries, so that whatever charge we get from these solar panels is stored in the batteries due to this charge controller. It controls the storage of the charge into the batteries. And once the charge is stored in the batteries, we connect an inverter, which converts it into AC. And now this AC can be connected to the loads inside the home. Now, the same application can be applied to the microgrid. Same. This one, we have a charge controller and converter stored in the battery, or maybe directly connecting to the inverter, and then inverter which converts DC into AC. And now this AC on the fly, it is not stored, or it can be stored in the battery from here. or it can directly be applied over here from inverter to the AC grid like this. So this inverter converts this DC from this DC to DC converter and sends it to the grid or anywhere else. The same application, but for a microgrid. Another application, this power converters can be used, or power electronic circuits can be used in cellular handset VLSI chip. So these are, let's say, this is a simple example, DC to DC converters are used. They are actually implemented on a chip. Because I have highlighted these blocks over here, these are the building blocks. So several different building blocks over here, they require different levels of voltages. So let's say this part requires 1 volt of supply. This requires 1.2 volts of supply. This one also requires 1.3 volts of supply, and so on. So this DC to DC converter actually converts this DC value, which is received from the input from some battery or something, and converts it into different levels. So this DC to DC converter has, it converts, let's say 5 volts from the battery, 5 volt to 1 volt and sends it to here, 5 volt to 1.2 volts and sends it to here, and to 1.3 volts and sends it to here, and so on. So these DC to DC converters are used in integrated chips, and let's say for this mobile phone handset, we can have about a dozen of DC to DC converters on a mobile phone. And all of these DC to DC converters, they are giving us the output or variable outputs, so that different components or different modules in the handset actually receive the required value of voltages. So this is an important application. Now another application is the electrical vehicle system. So battery cars or electrical vehicles, they also use these. So a battery is running the motors and engine and all this. So this is the power electronic converter or power electronic system over here, which gets supply from battery and runs the motor to run the vehicle. Okay, to finish, I think we must just discuss in brief about the types of devices. We already know different semiconductor devices, because basically everybody knows about materials used in semiconductor devices, basically silicon and germanium, everybody knows of. Other materials are also used in power electronics, silicon carbide and gallium nitride. So devices using these materials are also used in power electronics, because gallium nitride devices, they are smaller and faster. So for high switching or high speed applications, they can be used. And they also cover a small area. They also have lower on-state resistance. Lower on-state resistance means when the device is turned on or is conducting, the resistance at that time when the device is conducting is very small, very low. So what is the significance? The significance is, if this on-state resistance is low, I square R losses will be low. Because R value is low, on-state resistance is low, then the power loss is also low. So these gallium nitride devices, they actually consume less amount of power while conducting. So in that case, low amount of power is lost, yielding high energy, high efficiency. So, and efficiency, we know that if losses are decreased, efficiency becomes higher based on the definition of efficiency. So the main idea is to make the losses as low as possible, to increase the efficiency as high as possible. So gallium nitride devices are used in some of the applications in power electronics. So these are the applications, because they are faster. So for high power, high efficiency and for high frequency or high speed applications, they can be used. Okay, so now we know of four types of material, at least for the third year students: silicon, germanium, gallium nitride, and silicon carbide. Okay, now losses in control devices such as SCRs, MOSFETs, BJTs, and all. Two types basically: conduction losses and switching losses. And in power diodes, again the same thing: conduction losses and switching losses. I have categorized these into two. The reason is because power diodes are not controlled devices. But still, I just classified it differently. The reason is maybe because if they are not controlled, maybe the conduction losses are a little bit different. The values will be different, but the concepts are same. So they also incur conduction losses and switching losses. And we'll see what are switching losses when we deal with the semiconductor devices. So the thing is, because if we are saying that these devices are ideal in nature, in practice here they are different, then we say that during off state, the power loss is minimized, or we can say negligible. We can neglect it. But in reality, they are not negligible. We have to include these power losses also in calculations. Because power loss, they lead to the efficiency. More power loss, less efficiency; less power loss, more efficiency. So if we neglect these power losses during off state, during reverse bias or off state, then we can just say that we are having an ideal value of efficiency. If we include this, then we have the actual value of efficiency. Okay, now summarizing. Power electronic circuits, we need to achieve, because we already studied in this lecture, that what we want to achieve using power electronics, that is high energy, high efficiency, that we have seen that power electronics can do that. Compactness means small size, lightweight or less weight. High reliability because of static in nature. Low cost, because semiconductor devices nowadays, or semiconductor technology nowadays, it's very easily available, so the costs are very low nowadays. So what, again summarizing what I said in the very first slide, that these prerequisites are required. So these engineering subjects normally will be applied in the study of the power electronics in our course. Circuit theory and analysis, semiconductor devices. So these knowledge, this one you have already studied in basic electrical. Semiconductor devices, basic, you have studied in basic electronics. Linear algebra you have studied in mathematics, because linear algebra is also required for analyzing the power and all the signals. And electrical technology like RLC, how RLC resistance, how these components can be analyzed, or how by changing the orientation and the configuration of these components, power factor or power can be changed. Then power factor, we have discussed about the power factor correction, that why it is important. Electrical devices, inductance, capacitance and all. Power and energy signals, phasors, AC and DC analysis. So these prerequisites you have already covered in your earlier classes, and these we will be using in study of power electronics. These are the companies dealing with power electronic devices. Okay, thank you.